Let me say a few words about what complexity science is, what I think it is. It's an attempt to try to make quantitative mathematical modeling of whatever system you can think of that is characterized with having huge numbers of components that interact. So it's the interaction that's the interesting part. A gas is also a system of huge number of particles, but you can understand a gas and its properties without taking into account that there's a little bit of interaction between the molecules. But in any other situation, well, actually already when you go to solids and liquids and so on, you need to take into account the interaction between the components, but you wouldn't necessarily call that a complex system in the sense that we think of it. Like you wouldn't call a liquid a complex system, although it is pretty difficult to understand. Because there has to be some extra feature, namely that something emerges, some new features that are clearly not there in the components. Well, you could already say that happens with liquid. The H2O molecule is probably not wet, right? But water is wet. So this maybe is an illustration of the new thing that emerges because of the interaction between the many components. And these kind of phenomena, emergent phenomena. Consciousness would be one, right? Consciousness is certainly not a feature of a single neuron. Well, music is clearly also an emergent phenomenon. Music, there is no music in a single node, not much. So as one of our most ambitious projects in terms of daring science, I would say, we do this analysis together with people from the Guildhall School of Music and Drama, and person, Bjørn Krutz, who is an expert on EEG, and two students who are learning, well, now one of them have already become a doctor, is doing the mathematics of complexity science, if you like. The focus here is to try to see if it is possible to capture some of the things that happens in the brain as you listen to music. Well, you'll see them again later. That's the team as just mentioned. So we'll focus on the interconnectedness. We use EEG measurements, so EEG techniques. It's all probably best to think of as a pilot project because we do it sort of as a spare hobby. And some of us do it more as a spare hobby than others. For instance, Bjørn Krutz lives in the Netherlands and brings over all the high sophisticated, very smart technology to do the EEG measurements for free. And he does it mainly, I think, because his father was a French horn player in the Berlin Philharmonics and feels attached to music. And David Dolan tried in his spare time as a professor at the Guildhall to participate and so on. So this is an excuse for the sort of preliminary status of the science I'm going to report. But nevertheless, the hope is, as a first pilot study, to see if it at all is possible using technology and mathematics and good musicians to understand a little bit better what happens as people experience music. So we focus, as I said, on interconnectedness, correlations, and try to figure out what are the right measures to look for. What is it that characterizes what happens? What happens when people improvise? So that's the focus of this specific study. The point is, of course, that improvisation is it's a huge thing in jazz, obviously. It's not so common any longer in classical music. So let me explain the different interest, the different people that participates in the project has. So I just mentioned we as scientists, mathematicians, physicists, complexity scientists are just curious about, can you actually handle such a complex system as experience of music? David Dolan, the pianist, is interested because he's a classical pianist. He's an expert on improvisation. He spent 7 years at the Paris Conservatoire before Yehiro Menuhin persuaded him to come to Britain, and he was very happy to do so, he tells me, because in France, at least in sort of high sophisticated conservatoire circles, they didn't accept improvisation and classical music was a valid combination. They actually saw it more like an excuse for not preparing yourself. Whereas in UK, in Britain, especially, and certainly especially at Guildhall, they're very excited about improvising. And he teaches a course on improvisation in classical music, which now he's done for 10, 15 years. And lots of people have been through it, and they, of course, like it very much. So the trio that we work with, and which you're going to hear a little bit of, has this as their specialty. So they'll go out and give performances where they'll ask the typical sort of chamber concert setting. So there'll be a small audience which they can communicate with, and they'll ask for a theme, and then they'll try to improvise on that. And this brings me to mention why Guildhall, as a research institution, which you probably know the conservatoires and music schools have been turned into fairly recently, are interested. So John Sloboda, which were also mentioned on the view graph of participants, is some people say the world leading, I think actually he probably introduced the field in modern time, music psychology. And he's also the director of research at Guildhall and overseer of their contribution to research. And their theme is understanding the audience. And of course, understanding why classical music perhaps is more interesting to look at when it's improvised might be an important thing if you, like for instance, the London Symphony Orchestra, which is next to the, well, also housed in the Barbican and therefore next to the Guildhall, experience this dwindling number of concert goers. They want to know how they can make it more lively. So this is an attempt to contribute to that, you could say, ambitious attempt in trying to identify and prove without any doubt that improvisation is a good thing, which I hurry to say you don't need to measure anything on. You can just listen. You'll experience it immediately. Okay, before I tell you what we try to do, I want to persuade you that there is good hope that this kind of technology, EEG measurements, is actually able to capture something as untouchable, so eerie, so difficult to describe as high cognitive processing. Here is an experiment by Adrian Burgess, who used to be a colleague here at Imperial. Now he's professor somewhere in Wales. He wanted to test an hypothesis that was suggested by two neuroscientists, probably late 80s, Turoni and Edelman, that conscious perception is connected with a higher level of of complexity in the brain. It's difficult to know exactly how you measure measures of complexity. That's still debated, but they had some ideas. And the experiment that Adrian and his colleagues did is a very beautiful one, I find. So that's why I mention it. This is, you cannot do it. You cannot do the experiment here, but this is a random dot stereogram. You may have tried them sometimes. You sit in front of them, and then if you manage to focus at the far distance, then all of a sudden, out of all this bewilderedness, pops out a three-dimensional picture. And you are not in doubt when you see it. I don't know what this is. It could be a locomotive or something. I don't think you can do it because it's a reproduction and it's the projector and everything. But if you can, tell me. Then they wire people up sitting in front of this, and the objects had to push a button when they realized they saw the picture. And they measured the EEG and recorded this measure of complexity of the EEG signal and found clearly an increase. So you see, which I find already is astonishing. The very, very subtle personal feeling of all of a sudden seeing something three-dimensional, right? That actually can be captured by something as clumsy as electrode glued onto your head and wires and transistors and amplifiers, and which is just the EEG machine. But there you are. There is certainly some signature. Another experiment that I'll come to in a moment is on music, done by Jyoti Bhattacharya from Goldsmith. But before that, I just need either to remind you or tell you that neuroscientists have this idea of breaking the signal into frequency bands. So all what I tell you is pretty standard, but not necessarily for that reason the end of the story. There's lots of controversy about the actual meaning of these frequency bands. So what I'm talking about is that you record the electrical signal from the brain, and that's of course some wiggly lines or whatever. You probably have seen EEG signals, lots of time signals floating up and down, and then you break it up into frequency bands. And people have from early on talked about these bands and their functionality. So delta has been found during some continuous attention task. I highlighted the ones that we want to look at later on. Alpha bands between 8 and 13 hertz is all pretty technical and a bit arbitrary, one have to say, because it has, these bands simply are historical, that they started to do these EEG experiments 100 years ago, and they had devices that could cover various frequency bands, and then they decided, some of the neuroscientists, that maybe some of our tasks are concentrated in some of these frequency bands. And this is not entirely clear how true that is. But anyway, alpha activity pops up when you are relaxing, and if you're thinking. If you do that sometimes, then it also comes up. And beta has to do with activity, anxious thinking, active concentration. To illustrate the truth value of these statements, I would say they're just taken from Wikipedia. So it's not that this might not change next year, right? But it is sort of the agreed standard at the moment, that this is how to interpret these. And maybe the important one here, gamma, very high frequencies, 30 and up. People believe they are particularly connected to short-term memory and matching of recognized objects. Keep that in mind, because in a moment I'll show you this paper by Joy Deeb and Helmut Petsche, where they look at EEG of musicians and non-musicians listening to music and speech. And this is fun. How many of you are musicians? Quite a number of you, so you can identify with the right-hand side. This bit is the non-musicians. What happens here is that the red shows a lot of activity, so that's how they interpret the EEG measurements in the brain in the different frequency bands. Here we look at Bach, Beethoven music text. The non-musicians get really excited if you tell them a story. They're not too excited by Bach, right? The musicians, they get a little bit activated in the delta when they hear Bach, but they don't listen to you if you tell them a story. If you now go to the gamma band, and that's what I told you, that people think is related to recognition. The musicians, the non-musicians, have no activity because they don't recognize it, right? They don't. First of all, I guess most non-musicians don't listen if you play music. They're so used to it that music is something that's just annoying in the background when you try to do your shopping. So they know how to turn that off. The musicians can't help it, right? They hear Bach. They've heard Bach since they were little, so the entire brain goes bananas. So again, to show that there's good hope, EEG seems to be very responsive to how the brain reacts to music. So here comes now the experiment that we did together with Guildhall. And as I said, we focused on correlations, and especially, which is, I think is new. I don't think anybody has really done that kind of EEG experiment before. We want to do something like this, right? We take an orchestra, wire them up to the EEG recorder. We take the concert hall, wire them up, and out comes the EEGs. So this is, if you just could get a little bit of funding, that's what we would like to do. Now, it's not exactly what we can do because we don't have any funding. So we have a trio. They get, each of them get a headset of electrodes, and we have 2 listeners. And they also wired up. So we have 5 people in total. And what then unfortunately happened is that turned out afterwards that the second listener, we have troubles with that. Again, because of lack of funding, we had 4 identical amplifiers and a 5th one. And the 5th one, you cannot synchronize it at the moment. You have to synchronize at millisecond level in order to do the mathematical analysis. So that's excluded from the story. At the moment, we have a concert orchestra consisting of 3 people and an audience of 1. But it's a beginning. Okay, so the idea is then that the musicians play the music, small pieces, in what we call strict mode. And I think that's a good word for what they do, although our referee decided we need to call it prepared. Otherwise, we'll never be able to publish this. So now we have to call it prepared, but I still think that strict is precisely what they're doing. So they just follow how the music is written, or if they improvise, actually they also improvise strict, they just improvise so that it follows music theory, nice harmonics, pleasant. And then they let go where they just go. Let go, right? They just try to express their feelings. So that's the two we want to compare. And we have this EEG team, as I keep mentioning, Björn Krutz and his assistant Anita Krutz and some assistants, and a big audience, but only one effectively wired up. So John Sloboda also did psychological testing of the audience by questionnaires, and I think we had about 20 in total. David Dolan, who oversaw and actually participated also in some of the experiments early on, but not the one I'm talking about right now, is there. And he's a very great musician. And here are the people you'll hear in a moment, the trio. Anima, they are students of David Dolan and very good at improvising. And here is the music that we tested. So Telemann and Ebert and Ravel, and then two pieces improvised, but in these two different modes, let's go and strict. And the analysis we then try to do is use the EEG, use standard software that clinicians in hospitals will use in order to identify, or rather try to identify where the signal you measure, where does it come from. And it's referred back then to the surface of the brain by mathematical analysis, and what should I call it? Labeled according to the so-called Brodmann regions. These are very old, 52, there are 52 of them named by Brodmann more than 100 years ago. And of course, you don't believe that 100 years ago, without any modern scanning techniques and so on, could explore and find out precisely the function of all these regions. But it's nevertheless used as a sort of geography of the brain, and people have their ideas about which region is involved in what kind of task. And then we do the experiment. It looks like this. See, it's very pleasant. Lots of electrodes and stuff. That's the drawback, because this was also, but that was a well-taken point by one of the referees, saying that we write in the paper that it's under normal concerts, in a normal concert situation. And this is actually a well-taken point, because, as you can imagine this chap here. He's a brilliant viola player, and he has a tendency to be very flamboyant, and then, of course, all the wires go. So this is, again, a problem of having not enough money, because you can easily get hold of wireless caps now, obviously, right? You just think of all the wireless stuff you have in our houses, and this is no problem, but they cost money. So that'll be when we want to do one day to do this in a more sophisticated way, a more professional way, it would be without all the wires, and that would let the musicians, of course, express themselves less hindered. Okay, and we now try to look at the comparison between let go and strict, and with a bit of luck. So that was a bit of Telemann played in one of these modes. You need to make up your own mind. We do it again, hopefully, in the other mode. So think for a moment about which one was which of these two recordings recorded the let go and which one recorded the strict. Do you have a feeling? You don't need to say anything, you can just make up your own mind, then I'll tell you. The first one was the let go and the second one the strict. And some people may have found it difficult to tell the difference, but the brain probably noticed it, nevertheless. Okay, so here is the this S-Loretta, as it's called, analysis of the output from the brains of the players. So of course, it's not very clear-cut. And it's not that you easily see the differences. So what we had to do here was to average over the three players and the different pieces they played in the two different modes and subtract one from the other and see what differences in brain activity came out. And this is then done in the different frequency bands. So what then Björn Krutsch decided for the alpha wave activity is that actively involved in sustained attention, working memory, and inhibition of response. Maybe the latter one is the funny one, or interesting one, surprising one. This says that in the let go, there's more what I have highlighted in bluish than in the strict. So there's more inhibition, for instance. If this is true, there's more working memory. That sounds reasonable, right? If you improvise, you probably need to use your memory rather than just play strict. Again, the players, but now in the beta band. So actively in the letting go, there's more involved in motivation and will. That's suggestive. We can do the exact same for the player, for the listener. And of course, we want to do it on as many listeners as possible, if we just could get around to it. And what is I don't know. You can make these conclusions, as I tell you, just by using standard technique, find out which brain areas are more activated in one mode than in the other, and look up what these brain areas in sort of folklore, neuroscience, is supposed to be involved with, and you can come up with these kind of conclusions that in the let-go mode for the musicians, planning and coordination of movements are more active. The listener are more actively engaged, more activity of areas responsible for executive functions, whereas cortical regions associated with self-awareness were less activated. Did you feel that? Did you float more in one of them than in the other? Then we can go a step further and use information theory to try to figure out how the flow of information, if you like, between the different electrodes are. And this is what Xiujian Wan is doing as part of her PhD. And I just want to flash this. I don't think we have the time or interest, perhaps, to go too much into the details, but there are standard mathematics that you can use to try to figure out how different time series are related. And people use the language of, call it information flow and so on. That's an interpretation, but at least you can mathematically check that it's directed, that the, let's call it information, flows from one time series, not to the other. And we use mutual information delayed, and then together with something that's called mixed embedding, developed by Blackloss and Kogiomtis in 2010. And this is part of the research project, of course, to see if some of these measures, which you can immediately imagine, if they actually work, are fantastically useful for many things, not least finance, for instance, but also finding other causalities or relatedness between whatever time series you might have, say global warming, or in health. So there is a lot of activity in this kind of activity where you have large time series, long time series, and you want to figure out, are they related? The number of storks and number of babies, for instance, are they related? Then we do a number of things we do between players. So here we have the 20 electrodes that are on total placed on the flute and the harp player. So we have the flute, how does that work? We have the flute and the harp. And then whatever is off the diagonal is flow from one to the other. So all this extra color indicates that this kind of mathematical measure of information in this particular moment goes from the flute to the harp. And then I don't know if you can see here. We can do that with time. So look at small time windows through the music and see how the musicians supposedly, according to the mathematical analysis, drives the other one. So if the curve here, it's a bad plot, and I realize the projector is not fantastic. But anyway, the idea is that you can by following these curves, see when the information is more flowing from the flute to the harp than from the harp to the flute. And of course, the idea would be, so let me just summarize it this way. So what we saw was that the harp is the one that drives the other musicians, by and large, most of the time. And this was a surprise. I don't know if you noticed the viola player, say the flamboyant person that sits in the middle. When you sit and look at it, you would have thought that he was sort of conducting the entire trio. But then the flutist said that he thought actually might be right, that without having thought too much about it, that the harp being, of course, a 10-finger instrument, and therefore being able to play the harmonics and set up the structure more than the other single-line instruments, that maybe the harp was actually what sort of anchored the music. This we want to check. Had we beforehand known that we could see this kind of flow, of course we would have done an experiment where we just have asked them to take turns, have arranged that beforehand, right, and not tell us who would be the leading musician, and then we would compare what the analysis gave with what they had decided to. The only check at the moment we have on this is that the information flow is from the musicians to the listeners. That's at least something, right? Had the mathematical analysis shown that the information flow was from the listener to the players, you wouldn't have believed it, would you? So, see, that's a little bit of a check. Then we can look at the flow of information. Yeah, that's what I actually told you. Between the brains, and here, the number of significant connections between these brains. And what we find is that there are more of them in the strict. This is a surprise to me, but maybe we can talk about that afterwards. Maybe it shows that you cannot trust the mathematical analysis, or maybe there is something happening in strict, that some coordination, some communication that I would have thought were more needed when you improvised. And you can look at the flow within a brain. That's what is happening here. And now we're a bit in trouble. We see that the musicians, and at least we have 3 of them, has more interconnectedness. What I show you is the difference between, again, the two modes of playing. And I show you the difference in the number of arrows, so links that are active. And you see that the musicians, again, have more of them in strict than let go now within the brain. Before I showed you there were more of these links between the different brains. But the one listener has more links in the brain when he listens to the let go mode, because these are now negative, and it's the strict minus let go. So there are more links inside the brain of the listener. And here, that's of course that's why I say this is only a pilot study, because we should have had exact same for the other listener, or for 10 listeners, right, to know if this is just that listener that has a strange behavior during let go, or this is the typical response that your brain becomes more connected when you listen to music that's improvised. Yeah. So I don't want to stress the conclusions very much. We can discuss them a little bit. The reason I don't want to is that they are very tentative. It's all very difficult to know how much attention you should pay to these interpretation of function from the Brodmann areas and so on. But there are differences. I want rather to spend the last few minutes on what you probably noticed, that of course the music varies. And then David Dolan, being a great musician, decided that there are some special moments. You know the tickling effect, right? When the hairs in your neck raises, that's when the music is particularly engaging. And we want to see if we, by this method, can tell the difference between these moments. Are there something different going on in the brain's processing than sort of overall just listening to the music? This is all very well, except that, let's see, I want to play the same if I'm lucky, in the other mode. Let's see, so I now understand that I have to do something. So that's smart. And then. You must be made of stone if you don't cry when you hear this. Isn't that true? It's just fantastic. And the most fantastic is apparently, according to the official data, the second one. That's the let go. And let me show you, if I can control my machine. Let's see. Yeah. So this is now what happens overall. Here we make the difference between activity in the musician's brain, or the musicians, there are 3 of them, and the listener's brain. And if there was no difference, if they are completely activated the same way, it will all be gray. So there is some difference, but not much actually, in the right-hand side. This is overall. But then look during the special moments. So just now focusing on these few special extracts. So we have a number of them. David Dolan had gone through and decided which of them are most heartbreaking. And then the 2 brains are much more in sync or similar or so on. Now there's only this little area here, Brodmann area number 7, which people believe is related to visual-spatial information processing. That's different. And it is, the more activity is in the players. I don't know if that makes sense. They probably have to do a lot of visual-spatial processing in order to get the music out as they like it. So yes, you can clearly see some difference. Whether it makes, or what sense it makes, I think it's still a bit open. But you can certainly see a difference between the overall play and then the moments, which makes the moments that you remember forever, right, when you think of a piece of music. Okay, so I'm nearly done. And I just want to say that the tentative conclusions are like this, that the letting go mode gave rise to an intensified executive functioning in the listener. And that, what should we say, that there is this decrease in self-awareness and this visual-spatial processing. One of the things that is interesting is, of course, that we see that the motor part of the brain, and people claim that about 75% of all processing in the brain is about motor, because otherwise you can't stand up and you have to breathe and your heart should beat, and there are lots of things to look after. And then so therefore, of course, the musicians that sit there and fiddle around, you would think their motor part is really, really highly activated. But it's actually the same for the listeners. And this is probably because they are looking. This has been seen in other experiments. If I see you hop, my hopping part starts to activate. And therefore, the obvious experiment that we should do is to listen to this without seeing the musicians. And again, if just not Bjørn Krutz was fantastically busy trying to survive also, I mean, he has to earn a salary like everyone else, we would do this experiment, because we can, of course, just play the music and then see if the listeners now have the same motor response as the musicians, which would tell us then that they have it during this session because they see the musicians move. Right? So what is the conclusion? Yeah, let's take the artistic one, which I think you maybe can sense that it's perhaps not needed, except in order to persuade the French Conservatoire in Paris that it's a good idea to improvise. It makes the music much more moving, much more exciting. And that's pretty clear, but I don't, and you can see that there's a difference, right? So that's the artistic conclusion that's been underpinned by both the psychological questionnaires that I haven't mentioned and the EEG analysis, if you like. And what I find, of course, when we look at it from complexity science viewpoint, that it is pretty marvelous, although it's clearly not conclusive how and what it means, how to analyze and what it means, what we find. But nevertheless, it's obvious that there seems to be a robust difference in the EEG, and therefore perhaps something we could develop to use in many other situations. And let me just remind you again, all the people that have been involved, not least the amazing trio. Thank you. That's it.